Hello and welcome. So, just going to jump right in. Today, we're going to be looking into gel electrophoresis and a little bit about restriction enzyme review. So, let's get going. So, here we have our gel electrophoresis set up. If you look up here in the top left, where our setup is, went back. So, this is similar to the Biorad power supply and the equipment that we will use in class. So we are going to fill our gels with samples, and we're going to load our gels into our apparatus here. And very important, where the holes in our gels or the sample wells go. These need to line up on the negative side of the chamber for a big reason. That most everything we deal with is going to be negative. And negatives and other negatives repel. So if we put the wells that are going to contain negatively charged samples on the side of the electrophoresis chamber that has the negative charge, these are going to repel, which is going to push our negative sample through our well towards the positives down there. So I want to tell you something that you may think you know, but you don't know. You may have been lied to your entire life. Everybody that deals with DC electricity, direct current, thinks that the flow goes from positive to negative, when in all actuality, the electrons that move, that causes the electric current, move from the highly concentrated electron side, which is the negative side, to the side with the less electrons, which would be the positive side. So electricity actually runs backwards from the way that everybody thinks it does, which I think is right. So this electric current, this negative current, is going to push our samples because the negatives are going to repel from each other. So it's going to push it down, and that positive is going to pull it to itself. Thinking about it like animals running through a very dense forest. So they're running, so our samples are moving through. They're moving negative to positive. But something's going to happen. As they move through the gel, the larger particles are going to get stuck. The smaller ones are going to be able to weave further, but them too will eventually get stuck. You can think about it like a increasingly dense forest. So as you go into the forest, it gets denser and denser. The big animals are not going to be able to maneuver between the trees. They're going to get stuck. Same thing with the gel. The bigger fragments, the bigger proteins, they're not going to be able to maneuver between the matrix of the gel. They're going to get stuck towards the side closest to the wells. And the smaller DNA fragments or the smaller proteins are going to be able to kind of shift their way through that gel and make it down further in the same time limit. Down here in the bottom left, you will see that this is kind of what a gel could look like. Now this is a little bit larger than gels we use, or it's oriented different, but you get the picture. So moving on. Oh, and then I forgot. In lane 1 here, you see there's a lot of bands. And this is going to be our ladder. This is our marker. So this is a standard sample that was designed in a lab, and we know how big every single piece is, how it will line itself up. And the reason we run this is so that all the other ones from our samples we can compare back to our ladder, kind of determine roughly what the size is. And these several uses for this you can see down here at the bottom. I'm not going to read them all to you for the sake of time. Moving on. So before we go further, real quick, let's review restriction enzymes. So some reminders. They're called also restriction endonucleases. They are from the immune system of prokaryotes. So if we look up here in the top right of our screen, we'll see the picture of the little spider-looking thing. So that is a bacteriophage, or a virus that attacks bacteria. They inject its DNA into the bacteria, which would hijack the cell and take over it and eventually lead to the death of the cell. And then, but if it releases these restriction enzymes, it will find codes on the DNA of that virus that it injected in and cut it. And once it cuts it, then it is no longer a threat. It will no longer hijack the cell. There are thousands of different restriction enzymes. Remember, it can cut in two different ways. It can cut in the sticky way, which we see down in the image right here with the Eco R1, which is what we want. This is more, beneficial to us to use to connect fragments of DNA. And then it can cut in the blunt, which is HAE3 here in our diagram. So this allows us to do genetic engineering. We can cut open DNA and remove a gene, or we can cut open DNA and add a gene, which is, genetic engineering. All right, so we're going to run through kind of a quick paper style example of this, a little bit old school, to kind of help you visualize the process as you move into the lab and do your first gel electrophoresis run. So what you see here in front of you is 3 DNA samples. They are all the same sample. It is plasmid PMH157 synthetic plasmid. This is a make-believe plasmid that I made up that has 157 base pairs. So all of our samples here hopefully have 157 base pairs. And they each one, so the top sample, even though they're all the same, they're going to be cut with a different restriction enzyme. So the first one is HEN3. Everywhere it finds this restriction site, it's going to make a sticky cut. So in this case, it's going to find 4 restriction sites, make 4 cuts, and it's going to leave us with 1, 2, 3, 4, 5 fragments. In the next line, that one's being cut by BAM-H1, which it found 2 restriction sites, makes 2 cuts, and leaves us with 3 fragments. And then down at the bottom, this last row, we have ALU1. It is going to make 12 cuts at 12 restriction sites and leave us with 13 fragments. And you can see down here at the table at the bottom how big each of those fragments would be. So, well, I didn't want to go that far yet. But we're going to kind of move on to a little whiteboard activity where you can see this in action. So bear with me just a second. All right, so here we have a gel drawn on the board, and we have our lanes at the top. We're not using lanes 5, 6, or 7, just 1 through 4. So I have printed out these codes, and I've cut out a standard. I've cut out the code that was cut by HEN3. I cut out the code that was cut by BAM-H1, and I cut out the code that was cut by ALU1. So when we do electrophoresis, we make sure we line these wells on our negative side and our positive down here, because we want the electricity to flow and we want it to push our negative particles through the gel. So they're all going to start in our wells, and then when we turn the electricity on, they're going to start to move down together. And they're all going to move together, and as they move, they're going to start to separate. The bigger ones are going to get stuck, and the smaller ones are going to make its way further. All right, so at this point, our gel has ran. All of our samples, all of our DNA fragments started in the wells. When we turned the voltage on and that current flowed through our gel, it pushed and pulled its way, and it made our fragments move. The big fragments got stuck in the matrix of the gel at the top, and the smaller ones were made it the furthest. So as you see, our particle size, our fragment size gets smaller as we go down the well. Now, in our first lane, our standard, it worked exactly like the rest of it, but because this was made in the lab, because this was made to make this pattern, we know how big each one of these sections are. We know that this is 100. We know what's 100, 50, 35, 25, 15, 10, 5, and 1. And specifically, we know this is in base pairs, which means there are 100 A's and T's, G's and C's, C's and G's, T's and A's in a line to make that size of the fragment. Another way that this could be listed is KBP. So if we're dealing with big numbers, in which case this would not be 100 base pairs, it'd be 100,000 base pairs, 50,000 base pairs, 35,000 base pairs. So it depends on the scale that you need as to what you would use. So now that we know the sizes of these, we can kind of compare them to what's around us, right? and we can kind of figure out or get close or estimate the size of the fragments that are here with us. So this does not line up with 100, so we could say, it's in 90, 91, 92 range, something like this. This one doesn't quite line up, so this fragment is a little larger than 50. This fragment's a little lower or smaller than 50, and so forth and so on as we move down the well. Now, something you can't really see real good down here, but what we happen is sometimes we have a lot of the same size. So if you have fragments of the same size, they're not going to go to different places. They're still going to get stuck in the same place as the things with the other same size. So what you'll see is that the band that we view is going to start to get easier to see or more pronounced if you're using the ultraviolet dyes, or it's going to be a thicker looking band. So the thicker our bands are doesn't mean anything to do with their size, but it tells us how much is there, with a thicker band meaning a lot and a very faint small band meaning a little bit. All right, so real quick, let's take a look at our gel. This is kind of a, if we would put it in the gel imager or whatnot, we might come out with a reading we can use on a computer or something like that. But so this is a representation of our gel that was behind us that we did on the board. Hopefully a little clearer to see. So in the top left here, we have our table that kind of lists the fragment size. So these fragment sizes would be like their true size, and then over here on the right on the gel is kind of where they would land. One thing to note is that if you were to add back up all of the fragment sizes, they would equal the original size of the plasmid or whatever it is that you are using. So if we look at our table, if I add up all the greens from the Hindi cuts, I get 157. If I add up all the yellow oranges from the BAM cuts, I get 157. The only thing that's not necessarily going to apply to that rule is our standard or our marker, because that is not, it did not start as the same DNA fragment. It was a standard generated in the lab, so it's not going to be the same. So some key points to remember is that the particles that get stuck in the top of the gel closest to the wells are going to be larger than the fragments and particles and proteins or whatever that make it further into the gel. The thickness of the band has nothing to do with the size of the particle, but it tells us how much is there. So down here in the bottom, you can see a couple of these bands at 6, 8, and 9. Because there is more of them, the band is thicker. Remember, the wells go on the negative. Electricity flows negative to positive, regardless of what you've been told. And then, so you can compare back to your standard to figure out your size. So I hope this kind of gives you a rundown, maybe an understanding of the mechanism behind how the electrophoresis is going to work and what we are looking at when we look at our results after the electrophoresis. All right, well, I'll catch y'all with the next video.